Hello, welcome at this presentation about tooling decisions are engineering decisions. Engineering is, or engineering sciences, is about translating basic physics things into practical realizations. That's what we call engineering. And in today's session, it's about machining engineering. And machining engineering is about translating company strategy, company goals into machining performance, and preferably measurable machining performance. And that's what we are going to talk about today. And this is the third session in a series of 5. And the first 2 sessions, we could say, were a bit, should I say, theory, about the theory. The session 1 was kind of a warning finger saying, be careful, tooling is important. Session 2 was the first step in defining a good tooling strategy for a company. The first step has to be taken by management. Management has to decide what is good for the company. Once that's decided, we come to the third step in the process, and the third step is about engineering. And in company language, engineering, that is what is done, and company by company it can be called different, but some companies call it production engineering, other companies call it planning and programming, where the NC programs are made. Other people call it work preparation department, whatever. It is the department where decisions are taken about when and how and who are we going to do to produce our work pieces. That's the engineering department. Next time we are going to talk about more practical stuff, but let's stay today into the engineering phase of the process. And I'm not alone. I'm here with two girls that take care about all the things in the background, Margarita and Libby. They make all the technology work for this type of sessions. And engineers, because if you ask people, what is a machining engineer? What is a production engineer? And I would say engineers are system designers. And it's perhaps big words. But what engineering does, as I already said, is they translate management-defined targets and goals for the company into practical stuff to be applied in the company so that the targets and the goals are realized. Now, part 1, as I said, was about tooling is important. And some people now perhaps will say, yeah, of course, tooling is important. But trust me, the sentiment very often, if you try to discover really in a company, the sentiment very often is that on management level, at least, people think machines are important because they are expensive. People are important because salary costs are high. And tools, the cost of an insert is €10. Tools are consumables, not important. And I challenged that in the first session, because tools are really important. Tools are actually the only place where the workpiece is in contact with the production equipment, the cutting edge. Tools are important, and you better spend some time on it, because if you don't do that, afterwards you kind of will be, allow me to use the word, punished for that. And if tools are important, and if tools should be handled in the correct way, everybody has to take his role in that. Management has a thing to do, engineering has a thing to do, and afterwards operators have some job to do. Management we already talked about in chapter 2, or in part 2 of this series, where we said the role of management is not about the details. Management does not have to decide on carbide grades and geometries and all that type of stuff, but management has to decide on what, on a company level, are important goals. What are the KPIs for the company? Is it productivity? Is it profit? Is it cost savings? Is it sustainability approaches? Whatever. That's up to management. Now in part 3 then, we come to the engineering side of it, and engineers, what they have to do is take what management decided as a target and define processes, systems, so that target is realized. And in part of those things, we have tooling. And this session is not about carbide grades and different types of geometries, because for that there are technical educations and technical trainings. What we are going to talk today about is how do we decide? And you know, let me give you an example. If suppose management did not do their job, and we leave it to the engineers to select tooling, to select processes, well, you are going to find your company full of Ferrari cars, and all those cars are going to be in a race to be fastest. That's the result if you leave it to engineers. They go for performance, they go for speed, it must be fast, they want to win the best possible, highest performance. And nothing wrong with that. But the question should be asked, imagine if we stay with cars, that somebody says, it would be handy to have a family car, because my wife or me, we have to take the children to school, and we have to do some shopping for groceries and so on. So we need a car in which there is room for children. There should be a trunk big enough to put the groceries in when we do shopping. And as most parking places in cities are rather small, the car should not be too big. And as mostly my wife is using the car and she doesn't really care about Ferraris and Lamborghinis, it must be a handy car for her. But she prefers red. Red is important for her. She wants a red car. Now, suddenly, the job for engineering is different. Engineering needs to find a small red car. The engine is not so important. It must be handy. There must be room for groceries and children. What we are going to talk today about is, okay, with that as a mission defined by management, how do we find such a car without going into details like brands and stuff like that? So it's not about how do you use a catalog this session, it's about how do we take decisions. And engineering, the role of engineering, they are in between company goals, what you see here in the picture to the left. I call it here production excellence, however or whatever you fill that in with. Production, we want to be the company or a company with high production excellence, company excellence. With other words, somewhere we want to be better than our competitors. So we can beat them and take a bigger part of the market. Nice, that's the company target. To the right in this picture, you have, okay, once we know what we are after for, we have to define machining strategies. We have to define tooling. We have to figure out cutting conditions and cutting data. And this is what engineering really does. It's taking company targets, translated into technical choices to be made, but as such that the target is fulfilled. In the bottom of this picture, or at the foundation of this picture, I could say, is workshop people. And that is something which is very often overlooked, because we will see next session when we talk about this, that whatever the company target is, and however good engineering translate that into strategies and tooling and cutting conditions, the reality will always interfere with the plan. And fixing that, that's the role of operators. So engineers somewhere must find a method, a system to interlock operators in their procedures. Operators are very important. But I'm going to come back to it. It's part of the game, those operators. And if you see it like this, what engineering does, it's not just selecting cutting tools. What engineering does is defining processes, defining process behavior, and see how we have to mix all the different elements in such a way that the target is achieved. And here we make kind of a jump, because in part one and in part two, and partly here, we talk about cutting tools. But somewhere we start talking about processes. And that's something you have to realize, really, and that is that the value of a cutting tool is only obvious, or is only coming to the surface when you put the tool in a certain environment, in a certain application. If you take whatever catalog, if you open the catalog, trust me, catalogs are full of good tools. If a tool would be bad, it wouldn't be in a catalog. But not every tool in that catalog is the best tool in a certain application, in a certain company. And that is why, before going into details like carbide grades and stuff, engineers need to take different types of decisions. The more overall decisions, the decisions that link tooling technology to machining technology and makes tooling technology part of machining technology. Now, it's a vice versa way, of course, but that is really what they have to do. And here I want to put something in between, because I have heard this, I think, a million times in all the years I'm in machining. When you start talking with engineers, and operators are ill in the same bed, you know, so often when you start talking about productivity and costs and profit and sustainability and stuff, a very traditional response from an engineer is, excuse me, I'm not an accountant, I'm a technician. And I find that so strange, that I don't know why, that kind of aggressive thing. I'm not an accountant. You hear sometimes from supplier side the same thing. If they talk about the tool and the technical stuff and so on, and the moment the customer asks, yeah, and what is the cost, they say, I don't know, I'm a technician. Don't talk me about costs. And yeah, of course, a machining engineer is not an accountant. I know that also. But what a machining engineer has to realize is that whatever decision he takes about whatever technical aspect of the tool or the machining process, there are consequences technically, but also economic, and also from a sustainability perspective. Because if an engineer takes a high-performing tool, I don't know what, with very high cutting conditions, and it's all very nice, but typical for such type of tools and applications is that there is high energy consumption. It's part of the game. And if in a company people are a little bit allergic to high energy consumption, that is going to have a kind of a conflict in it. The engineer goes for, let me call it, high energy consumption solutions, while the company is chasing low energy solutions. And of course, the engineer can say, yeah, that's not my concern. But it is his concern, because it's his decisions that decide on those things. And what engineers they are confronted with, and here I tried a little bit to group company targets in 5 or 4, or I don't know, families, because every company has different targets, obviously, because every company is unique. But if you listen to the targets they have in companies, targets can be about productivity. It's about time. Produce a lot in a certain time, produce some in shorter time. The moment people start discussing time, productivity is what they are after. And if productivity is what you are after, you need tools that perform. If I talk about a car, if speed is what you want, you need the car which is capable of reaching high speeds. Makes sense, I think. In other situations, it could be that companies go more for the cost perspective, the profit perspective. And it could be in one company at different moments in time that they have different situations. But if a company goes primarily for economy, that means that if you look to machining processes, the target is not speed, but cost. And if I translate it to a car, if you say we need a family car with the lowest cost possible, perhaps you should go for an electric city car instead of a high-performing Ferrari car with a V8 engine in it. It's a different target. Other companies, they go, a third family is about quality. Full quality. We can deliver high quality in workpiece quality, tolerances and roughnesses and dimensional things and stuff. Could also be quality in keeping one's promises. If you promise to a customer tomorrow the work will be done, quality is also that the work is done tomorrow. That is another approach to a machining production. It's quality. And if quality is what you want, reliability of processes is very important. Security is very important. And for a car, it's the safety things around the car that are the major decision point. Speed is lesser a problem. That it's a little bit more expensive is perhaps lesser a problem, as long as it has the highest possible security stuff on board. For machining, it's the same thing. It's about reliability. It's about keeping your promises. It's about delivery on time. It's about quality on time, and so on. And tooling then is also here a different approach. Here we need stable tooling, robust tooling, reliable tooling. The fourth family is about versatility. A company can say, look, to their customers, whatever you ask us in the morning, we deliver in the afternoon. If tomorrow it's stainless steel, we don't matter. If the day after it's titanium, if the day after it's... We deliver whatever in time. That is about versatility. We are flexible. We can handle different situations in a fast way. It's again another approach. And if you think about tooling, here it's about tooling which is versatile. So I don't lose time in between two different types of workpieces in having to reselect all tooling and cutting conditions and stuff like that. I want tooling with a broad application domain. That's what we want here. And then the fifth one, that's why I was doubting a little bit between 4 and 5 families, because very often sustainability is presented as a fifth approach. I don't think that's correct, because, sustainability is kind of, if you manage in such a way that you have the best possible combinations of all 4, the correct performance level, the correct cost level, the correct reliability in your processes, and the ability to handle smaller batches. If you combine that, I call that you have a sustainable approach to your machining process. So sustainability is not really, in my eyes, a fifth family. It's a combination of the 4 previous ones. Now, engineers have to handle interactions, because true results are depending on interactions between different elements. If you go for a strong geometry and you combine that with conservative cutting data, it won't work. If you go for a sharp geometry and you combine that with aggressive cutting data, it won't work either. So it's not about every element on an island. It's about how do things interact. So an engineer should be careful not to have a too focused look. He should keep a broad look on things. And broad look means that it's not only about technical stuff, as I already said, but also about being aware of the economic dimension to it. If you decide to change a cutting speed because from a technical perspective that would be better, nice. But there are other consequences to that also. Some of them are economic, because higher cutting speeds, lower tool life, you need to buy more tools. As a very simple example. There are sustainability things to remember, because if you take the wrong geometry, if you select the wrong geometry, you could end up with higher cutting forces, and higher cutting forces means that you need more energy. If you have an unreliable machining process, it could be that you end up with wrong workpieces and that you have to scrap them or that you have to rework them, which is waste. And waste is what it's about when we talk about sustainability. Now, going back to this picture, where to start, because it kind of all links together. Obviously, it starts with company targets. The role of management, you remember? Management decides company targets. Then engineers have to decide tooling strategies, machining strategies, and cutting conditions. I think that machining strategies should be the first choice. Second choice is make sure you come to a tooling selection that makes that it can be applied in that machining strategy. And cutting conditions are kind of the flexible thing here, because if you have a physical tool, how it works, you will influence by how you select cutting conditions. For me, that makes sense to do it in that order. What is wanted by the company? What is the definition of production excellence in a certain environment, company? How do we select machining strategies for that? How do we make that tooling is correct to be applied in those machining strategies, and use your cutting data as a connection element between the two? Operators are always there and should be kept in mind. And I think that the first step, kind of, is that before optimizing, because people always like optimize this, optimize that. First, it's about stability, and what engineers first have to decide, once they have decided on a strategy and a tool, is for that combination tool in a strategy, what is the window, kind of where we can use the tool in concerning cutting conditions. So the tool acts as a stable element in the machining process. And to achieve that, once again, an engineer should have a look at all the elements, not just one. Optimizing a cutting speed is a nice objective, but if you do that, you have to keep your eyes on all the other stuff around it. You have to be aware of that things are related to each other. And that keeping an eye on, because things are related, means that typical in engineering is that an engineer has to decide on trade-offs. Kind of, if I go for something, something else will. And if that is not good, then I trade-offs, relations. And one of the trade-offs is a very typical one, the workpiece material and the cutting material. Those two needs to be compatible. And if a workpiece material is something, then a good cutting material will be something else. And at first sight, one could say, yeah, okay, makes sense. For steel, I use this cutting material, and for stainless steel, I use that cutting material, and so on. However, if the company target is flexibility, then we will be confronted with a situation where we say, okay, I have to machine as well steel, as stainless steel, as titanium. And depending on what the company wants, performance or productivity, or flexibility, which cutting materials to be selected, it will be a trade-off. You can go for one cutting material that can be used in all three workpiece materials. That's very nice for the versatility approach, but from a performance approach, it's perhaps not the best solution, because the best solution from a performance approach would be for every individual material a different carbide grade, a different cutting material. But that would mean that from a flexibility perspective, it's less handy to have all those different types of carbide grades in the company. And that is a trade-off engineering has to take decisions in. Another trade-off is long tool life of high productivity. That's a classic one in machining. If whatever tool you use, you want to have a high tool life, long tool life, you have to reduce your cutting conditions, but reducing your cutting conditions means your productivity goes down. You need more time to do the same output. If you want to reduce the time to create output, you have to increase your cutting data, but your cutting data means automatically that your tool life of the tool you have will be shorter. A decision to take. The third trade-off is, do you want to have peak performing cutting data, or do you want to have stable cutting data? And here I would like to remind everybody on a typical engineering practice. Engineering practice says, or that typical engineering practice says, you find out what the maximum is and then you reduce it by 30%, just to be safe. Have ever considered doing this in machining? You find out what the maximum cutting speed is you can run a certain tool in a certain material in, and then you reduce it by 30%. Just to be safe, just to have a stable process. Do you always want to be on the edge or in a stable situation? A decision to take, but if you reduce by 30%, there will be consequences. Your performance goes down by X%. Acceptable or not, an engineering decision to be taken. Cost versus performance. If you look to the process itself, do you want to produce your workpieces as cheap as possible so you can, with a reasonable profit margin, have a sharp market price and attract more customers? Or do you go for high performance machining so you can produce in a shorter time more workpieces and use that as an attraction pole for customers? Two different approaches from a process perspective, and of course, depending on where you put your priorities, tooling will have to follow. And the fifth one is about supply chain. This is about suppliers and this is about delivery. Because if you go for high performance, you need specific high performing tools. And perhaps somewhere you end up in custom made tools. But if you go that way, you have to take into consideration that your supply chain is getting more fragile, breakable. And yeah, if you don't want that, you have to stay away from custom made tools. You have to go for the standardized tools you find all over. It's also an engineering decision. And this fifth one, sometimes engineers forget a little bit. Oh, I want this special tool best possible and so on. Yeah, but think about supply chain considerations in that perspective. In the end, every tooling decision is a compromise between things. The big question is, if the compromise is a deliberate one, is the one you want, or is it be created by coincidence? A typical example here is cutting geometries versus cutting materials. In the past, kind of as a teaser, I was sometimes, when I was doing technical seminars and so on, I asked participants in a call, what's most important, cutting material or geometry? Mostly people fell in the trap, if I can say so. First of all, both are important. The difference is the sequence in which you select them. And very typical for machining engineers is they start by cutting materials. After the cutting materials, they select all the other stuff, the geometries, the dimensions, the edge treatment, whatever. And then in third step, they select cutting data, which is very typical done. And it grew like that from a historical perspective. But for me, based on my experience, and I don't think I'm the only one with this, I'm not so special in this, but the first selection point should always be geometry. The geometry truly is defining how the process is going. And once the geometry is selected in the best possible way, whatever the targets are you have, then you select the cutting material, and the cutting material is kind of the sustainability factor to the geometry. The cutting material must make sure that the geometry, the cutting geometry, stays as long as possible fully operational. That's the role of a cutting material. The geometry defines how the interaction takes place between workpiece and cutting edge. The cutting material preserves the cutting edge or the cutting geometry for the longest possible time. And if they are fully working together, then you have truly a stable, wear-resistant, high-performing cutting tool. So if you want to have sustainable machining, if that is your target, you have to understand this relation really. The geometry defines the physics of machining, the cutting forces, cutting power, energy, ship formation, whatever. All of that is defined by the geometry in the process. And if what you see is not good, you have to play with geometries. Once you have a geometry which is to the best possible working, then you select the cutting material that supports the geometry in the best possible way. With other words, that add wear resistance, thermal resistance to the tool. So the geometry can do its job as long as possible. And if both of them are fully aligned, again, that's the moment you have your stable, robust, reliable, sustainable machining process. And you see, we have been talking about the performance of a cutting tool, and we haven't been mentioning one single carbide grade or one single cutting geometry. We have been thinking in a general way. So decision making in machining is prior to filling in the details. That's perhaps the main message I have here today. Now, if we look to engineers, machining engineers, programmers, planners, there are some discussions, but I would say, my experience again, in general, the average engineer is rather knowledgeable about a machining process and what's going on and stuff. But what I also find is that if there are problems, most of the problems are related to behavior, to attitude, to mindset. And if based on that the wrong decisions are taken, yeah, you all know the consequences. Unreliable machining processes, scrapped workpieces, broken tools, and so on. And you know, typical mistakes, pitfalls, is over-engineering. Just to prove it can be done. The drawing says a tolerance of 1/10 of a millimeter, but the engineer is going to decide a strategy, so the tolerance in which the workpiece is finished is 1/100th of a millimeter, just to prove we are capable of doing it. Now, it's all very nice from a tradesman's perspective to be proud, look what I can do. But from a company perspective, it's over-engineered. It was not needed for. Money and time has been spent on something which is basically of no value for a customer. So most probably the customer doesn't want to pay extra for it because he didn't ask for it. Chasing their own KPIs. But that's perhaps more a communication thing between management and engineering. If management is thinking in terms of cost savings and engineering, very typical, goes for high performance, yeah, there will be a conflict in the future. Or perhaps the near future even. So optimizing certain KPIs, performance, costs, quality, versatility, sustainability, all very nice, but make sure you optimize the right ones, the correct ones for the company. And a third thing is changing everything at the same time. Looking at the process, the thing doesn't go as we thought, and then we start changing the tool and the cutting conditions and the machining strategy, everything at the same time. And sooner or later you find a solution, but in the end, nobody knows what was the true solution, what truly solved the problem. Was it the tool? Was it a change in cutting conditions? Was it a different? I don't know. One at a time. An important one. Ignoring or even rejecting feedback from operations, feedback from the workshop. Because I hope I don't offend anybody, but it's so typical in a machining company that engineering thinks operators are stupid and operators thinks engineers are stupid. And instead of talking to each other, they kind of refuse to say anything. Feedback from reality is so important. On the other hand, for people in reality, people in the workshop, feedback to them about why did we select certain things is also important. Remember, feedback goes in two directions. Good feedback goes in two directions. The next one is, treating every problem as a tooling problem. You know the saying, if every problem is a nail, the only thing to solve it is a hammer. Not every problem is a tooling problem. Also their engineering should realize that they are responsible for the system. And tooling is part of the system, but there are other elements in the system. And if the system fails, it's not always the tool. It could be another reason. And, overall, I think engineering is responsible for bringing calm in a production process, not complexity. That's very important to realize. And then there are the organizational things, engineering versus purchasing. Purchasing wants to buy cheap, engineering wants to have the highest performing tools. Company KPIs, tooling KPIs, which are not in line. Short-term fixes. There is a problem, we fix it, and we think, okay, it's okay now. It works. Today it works. Tomorrow we see tomorrow. And after a while having a multitude of different tools in the company, because every engineering decision goes into a different direction concerning tooling. Here it's about discipline. And if discipline is not there, of course the system drifts away into chaos. And the discipline of stable engineering is define the data windows, cutting data windows where the process is stable. Document your decisions so you know tomorrow, next week, next month why you took today a decision. So you don't need You don't take every single day another decision. Rationalize where possible, standardize where possible, review systematically. The famous machining thing, we did it for 30 years like that, so it's good for the next 30 years also. Review systematically. I don't say change systematically. I say review systematically. Perhaps there is need for change. And if you have these disciplines, you end up with repeatable processes, which is so important to have sustainable machining processes that you can repeat things. Sometimes engineers tell me, yeah, but the operators, they don't tell me anything. Yeah, but ask yourself your questions. Did you motivate them to give feedback? Did you listen to the feedback? Did you take care of that feedback and translate it back to management also? Perhaps it was a management decision that needs to be questioned based on the feedback coming from operators. So an engineer should not be afraid of taking operator feedback and take it to the management table. Reward feedback. Most of the time, feedback is punished, is blamed. No, reward feedback. Thank you for your feedback. And use feedback to refine things in the future. The real responsibility kind of everything together. An engineer translates a theoretical strategy into a practical reality. He has to balance things: performance, cost, sustainability, quality, flexibility. He has to find best possible balance, but whatever he does, he has to make it utmost to protect that there is a stable process, a repeatable process. And the role of tooling in this is not the cheapest one, not the best performing. A tool should be the stabilizing effect in the process and creates sustainability in the process. And in that respect, if you talk about excellence, engineering excellence should not be measured by optimization, but should be measured by controllable, repeatable, sustainable performance. And that means that, in a couple of words, what is the lesson to be learned from engineering? If engineering does isolated optimization, stop with that. Engineering is about a system. Engineering is not about one element. It's not about just the cutting speed. It's about the full system. And engineering should continue to develop, to have insight, to have knowledge about the physics of machining. Because engineering stands there for translating those physics into such a way that the company targets are reached. And the overall target for engineering is predictable excellence, not, as I put it here, occasional brilliance. It's not about winning one game. It's about becoming the champion, and that is not just one game. Engineering should create stability, not complexity, not unique brilliance. That's kind of what I try to say. Engineering is a translation layer. That's what I try to communicate to you. Management has to decide on the strategy. Operations later on has to execute. In between, in the middle, you have engineering, translating strategy into reality, but also bringing results from reality back to strategy. Engineering is a bridge. Engineering should create robust, sustainable, stable performance, not just one single extremely excellent application. And engineering should not create complexity, but should bring calm into a production, not chaos. And in engineering departments, my experience is that it's not about knowledge. Most of the machining engineers or planners or programmers or whatever you call it in your company I met in my years in the industry, they are rather knowledgeable. There's always room for improvement, but they are rather knowledgeable. They know what they talk about, but it's more the mindset, the attitude or the behavior. I don't know what is the correct word here, but engineers by tradition they want to prove things in the performance thing, and it's okay, but it's not always what companies are after. Most companies are after, first of all, sustainable solutions, not unique, one of a time, high performance thing, and the next day it collapses. With all that in mind, in the end, it comes to, and here you see just an example of, I call it the decision table. Most probably you can't read anything of what you see on the screen here. But what I try to give you here as an example, and if you are interested in this type of decision table, but if you are interested in a copy of this presentation altogether or some other information you would like to have, just let us know. Send us an email, put it in comments, whatever. And of course, all of this is available, this table and others, where I try to take all these things now about decisions. On this table, first of all, you don't find one single carbide grade, geometry, milling, cutter, turning tool, drill by name. It's all generic. But this forms the basis of engineering sciences in machining. An engineer has to decide about which machine spindle interface, tool holding system, type of tooling, cooling strategy, cutting material, cutting geometry, measuring, presetting, tool logistics, standardization, all engineering stuff, the vertical things here in the table. And a company management input, the horizontal thing, is chasing or cost efficiency or time efficiency or total quality or flexibility and variability or sustainability and circularity or whatever combination of these things. And what you find here then are guidelines. If you talk about one technical feature of a tool, how do you connect it to the spindle in a milling machine, for instance? And then the choice an engineer has to make is, do I go for an ISO connection or a BT or a CAPTO or whatever type of connection? Well, that thing is not just technical about torque and bending and stuff. That thing also relates to company targets. And what you find here are guidelines in that respect. And here you can define kind of a best tool. And then it's up to you to take that as a description, to have a talk with the people in the tool crib in your company or with suppliers and say, okay, this is my little red car with room for children and grocery shop things. And it should be handy so I can park it in a small parking place. This is what I need. Give me something that answers to this description. A lot of things are available also, as I already said. If you want to have a copy of this or other stuff, just let us know. And whatever we can help you with, of course, we will send. Time to see if there are any questions that came. How I'm reading now. How should engineering cooperate with purchasing without sacrificing machining performance? Can cost reduction and process reliability truly work together? Yeah, that's two questions. How should engineering cooperate with purchasing? The answer there is simple. Management should do its job and define and communicate company targets so that both purchasing and engineering or production knows what is demanded for. And that should be very clear, and that should a professional purchaser or a professional engineer will know then how to handle things and work together. The first question is management. If an engineer says, yeah, I can't work together with purchasing because they chase other targets, or purchasing says, yeah, in production they always want very expensive tools and I have a very little budget. Yeah, that's management. And the second question, cost reduction and process reliability work. Yeah, of course it can. It's all depending on the basic choice of tool, but very important also. It's very much depending on the cutting conditions you select. Yeah, we have some time more. Another question here is, how do you build tooling strategies that can survive staff changes, especially when experienced people retire or move on? Yeah. Document. And it's I admit it's a bit difficult. The typical machining expert is somebody who kind of like, how should I say this in a polite way, protect his secrets. Every machining expert has a very big level of knowledge, but sharing that knowledge is something he or she prefers not to do. And then indeed you have the problem that if people leave the company or whatever, that the experience leaves the company. And there's only one solution to that, and that is also a management solution. Very strange. Here questions are asked about the role of management, not engineers. But part of the job of an engineer or an operator is to document his or her expertise, experience. So it is protected for the company. And it's easily said than done. I know, because if you talk then to a machining expert, a very typical answer you will get if you ask a machining expert how to avoid vibrations, you know what he's going to answer, he or she is going to answer, that depends. With other words, I don't want to tell you. And then the challenge is, to try to find out anyway, what exactly does he or she means with it depends. Because the moment he or she communicates that, you have your variables in the equation. If you say, that depends on the material, here you have a variable. If you want to understand vibrations, you have to know the workpiece material, as an example. We have some more time. Why do many companies still struggle to reuse proven machining knowledge even after decades of production experience? Also a good question, and part of the answer is the previous one. Machining people keep their knowledge a bit secret, so reusing it is kind of impossible. Another thing is that people kind of a typical, what is typical? An average machining engineer is somebody always looking for new solutions. And that meaning, and it's a bit controversial, if you talk to machining people, on the one hand, you will have a remark from them, if you ask, why do you do it like that? They will say, we did it always like that, so it's okay. And on the other hand, if you ask them, why do you want a new tool? They will say, but we want to improve things, so we need new tools. Every day they need new tools. And as a conflict, or that conflict creates that experience there is not really validated for the future. Also here, I would say, if you struggle with that, here management again plays an important role. Perhaps you should bring outsiders to this, just to make sure that yeah, not too much company politics interfere with the process here. Okay, one last question. How do you convince management again? How do you convince management that tooling decisions are strategic business decisions, not just technical details on the shop floor? Yeah, that's a good one. Believe me, that's not easy. As an outsider in companies, I have struggled with that also a lot. That I know the importance of tooling. And I think if you really want to treat tooling in the best possible way in a machining company, it starts at management. And that means that as an outsider, I always wanted to talk first with management. But if you manage to have an appointment with management and they say, yeah, who are you and what do you want to talk about? And I say, okay, I want to talk about tooling. They say, oh, that's not my thing. That's not my thing. I'm not going over the tooling. Talk to the experts. And already there you have the issue that in the head of management, machines are important, as I already said in the introduction, because they are expensive. And people are important because, yeah, salary costs and stuff, But tools, little yellow triangles, more or less 1 centimeter, something. They call it an insert, I think. It costs €10. Talk to the specialists. They help you further on. And kind of the one who asked the question here, I would say, invite management to have a look at these sessions, starting with session 1. Why is tooling really important in company strategy, or an important element to make sure the company strategy is realized? And I know it's a battle. And I know you need to be perseverant and you need to insist, and sooner or later, hopefully, yeah, there will be some light. The other thing is more confrontational. If you talk to a manager and if you ask him, can I visit the workshop? And most probably will say yes, because most people are proud on their workshop and they want to talk about the new machine and the 5-axis milling machine and the 3D measuring thing and so on. But the only remark you have to make, the very stupid remark, is, my God, half of your machines are standing still and it's a very big chaos here in the workshop. You'll have his attention. But it's a bit confrontational. The other questions I take in comments and give the answers there, because I have to keep my eyes on the clock. Thank you again for being here. In core, the message I try to bring is engineering or programming or planning or work prep or whatever. They translate company strategy into machining strategy / tooling decisions / cutting conditions, cutting data, and so on. In that translation, they should aim for stability first. Stability, sustainability. That's first priority. Bring calm. Don't create complexity. Don't create chaos. Once the stability is there, then you could go for individual optimization by defining, working with different elements. But engineering, in doing that, stable stable operating windows, tool features, strategy, machining data balanced in a correct way, document everything so it's saved for the future. Listen to operators because they mostly want to give feedback, and that feedback tells you how good reality reacts on your plan, and if not, how to change your plan. And in the end, you can fine tune, you can optimize, you can improve a little bit this, a little bit that, as long as you stay within the stability window. Once that is done, we are ready for the next step, and that's going to be the next presentation also, where we want to talk about the role of operations in the picture, the role of operators. Because now we are in a situation that everybody in the company knows tooling is important. Management decided what is important for the company and communicated that to engineering, so engineering could take the correct production decisions. And now those decisions are entering the workshop, and the operations is going to apply them. What's the role of operators? First of all, I don't believe in what we call button pushers, the production monkeys. I think in machining, especially today, and the role of an operator is much more valuable than that, much more important than that. But that's the subject for next session, which is planned for beginning of July. I hope to see you there also, so we can continue the journey together and figure out the role of operators in the process of creating excellent production so the full machining company is successful.